Hi there and welcome to another tutorial. Today we're going to be looking at how to model and analyze a rigging structure. So we're going to use suspended cables to simulate lifting a sort of A-frame or some sort of small mechanical unit using an anchor point and some cables. So we're going to start with a clean blank canvas, opening up SkyCiv Structural 3D and starting with the units set to imperial, so I can see that in this bottom corner. I can change that to metric if I'd like, but for now let's use the imperial unit system. And I'm just going to start by plotting the nodes of the base or the frame that we're going to be lifting. So I'll just start just at the origin, and I'm going to use the pen tool. I always find this is a nice easy one just to map out and draw my members. So we're going to do a 4-foot frame, like a 4x10 or something like that. Let's go pick up that adjacent node, click that, and then we'll build up another 5-foot, something like that. It's quite a slender one. I can actually show you how to modify that as well, but for now just going to finish outlining the structure. Yeah, I just find the pen tool is good for that purpose, outlining, and then if you want to make any modifications, I'll show you how we can do that quite easily. I'm just hovering over the escape key. It's just an easy way to break out if I want to stop using that particular node as a reference point. You can see when I hover over the node, it's using node 7 as a reference point. If I want to cancel that, I just hit escape. And then to break out of the pen tool, I can just hit escape twice, and that'll go back to my default tool. So a few little shortcuts there that make it quite handy to use. And then we're going to also just demonstrate how if this might be a bit slender, we want to increase the width of this frame. Just highlight, select all my nodes, and it's picked up that the Z is the common input at -4. So let's extend that out to say 6 foot. So I got something like that. Okay, so we've got a little bit of base forming there. We're going to just simply provide some section properties to this. We're going to use the libraries sections, so we're going to just open up quickly load, so the quick load section, and we'll select the American AISC. We'll do some W shape, maybe something a little smaller, so W6x9. Submit that. That's going to load from the library, and we can just have a quick look at not repair, we want to have a quick look at the renderer just to see what we've built. So something pretty simple. It's going to be a simple frame, and the main purpose of this demonstration is to demonstrate how to analyze the cable elements that are going to lift up this structure. So I'll just go back to the wireframe, and a couple of different ways that we can place a node at this middle span of the structure. Simple one is just to split this member, so split it by 50%, so that'll give us the intersection there. Maybe split this one, and then once again using our pen tool just to give me a location or a node at that point, and then kind of coming up from there. And I can also turn off connect members, so this will just allow me just to plot a node. So let's go 10 foot up, so let's just plot a node at that top there. And if I want to undo some of these other things, I can just delete them. I can also rejoin these members, so kind of undo the changes I made just by selecting those two members and hitting join. Do the same here. I can also just hit J and then remove these redundant nodes. So obviously that's just put a node at the center, and that's going to be our anchor point of where we're going to connect the cables. And yeah, let's start defining where those cables are. So we're going to just click from here to join. Actually, that member is getting in the way. another thing we can do if that's not working. So the reason that is it's interfering with this member here. So what we can do is just go back to the default tool and just drag between those two nodes. And a third way we can do is just connect the members just in this left panel, just by going 12 to 6 and then 12 to 5. Okay, so we've kind of outlined the geometry. If we have a look now, we'll see that they are still using the same section ID as the base or the frame. So obviously we want to change that, so we're going to introduce a new section, and the way we're going to do that is just holding Control and going from left to right to select just these members here, so just the cable members that we want to assign a cable to. So then I'll click Members, and this is going to allow me to multi-edit these members. Same way I multi-edited the nodes, I'm multi-editing the members just by highlighting them and selecting members. And here we're going to make a few different changes. We're going to change this to being a cable, and we're going to create a new section ID, which is section ID 2. And we're also just going to review whether there was any advanced settings, which in this case there's not, but important to just review those, make sure that there's no missing information that we need to collect. But from here we have assigned the cables, these members to being cables, and introduced a new section ID. So yes, we'll confirm those. You can see that automatically the node fixities have also changed to pin, so that's quite an important part of cable analysis. And I can confirm that just by hovering over these little nodes to tell me that at either end we have now released the end fixities in rotation. So they're no longer rigid connections, which makes sense because it's a cable. They're usually connected by some sort of a hinge joint. Okay, so we now have a second section identified, which is denoted by these green members, and we're going to provide some information about these cables. So I'm just going to click that section 2, and we're going to define the cross section, and we're just going to use a circular shape, and we'll do sort of maybe a 2-inch cable. It's quite a large one. Let's try maybe a 1-inch cable. It's a 1-inch diameter. Just review the materials. So we've got structural steel. The manufacturing process doesn't matter too much. That's more for the design standards, which we won't be using here. We're just going to be analyzing the cable elements. So I'm pretty happy with the structural steel. If I wanted to introduce a different steel grade, I can do that through the library by either searching or scrolling through these or browsing through these different options available. So quite a few different materials we have in the database, so we can select one of these depending on the type of steel that we're using. But for now I'm just going to use a standard steel, which has a Young modulus of 29,000 KSI and some yield and ultimate strength properties. So submitting that, and then now we can review the renderer. That's looking a little bit more like the type of structure we want to analyze, and we can see the cable elements clearly defined there in the model. Finally, we want to add support here. So this is obviously going to be the support of our structure, and we're just going to add that to the 12th node, and just apply a pinned connection. And we're going to try and perform an analysis and kind of review the process of performing analysis and then repairing any changes that we need to make to our model to get it to a successful solve. So we're just going to start with a pin support. It might not be enough restraint, but we should be able to kind of troubleshoot the model if need be. Okay, so I've added my geometry, I've added my cable elements and my supports. Next we're going to apply just some loads. So maybe this structure has some equipment on it, so we can add an area load to apply to this base here. So we'll do 1, 2, 3, 4. So they're just the corner nodes of where I'm going to apply an area load. And maybe there's a 0.25 KSF pressure there in the global y-axis. And we're going to apply this actually, let's do a two-way load here. So we're going to apply it to all 4 edges. And let's call this equipment. Okay, so we've got some pressure being applied there, and if we review the equivalent area loads, we can see how that's been distributed. It's already automatically calculated the tributary areas and applied them as distributed loads. Really useful just to click this and get an idea of my variance. So that's a really good indication that all the pressure has been applied to those members correctly. So it's basically a kind of logic check to make sure that all the area, so the area times pressure, is equal to the sum of all these distributed forces, just to make sure that the two-way automatic load generator is applying that correctly. I'm also going to color my different load groups. So we'll see as we apply different types of loads, we'll have different load colors to denote those different load groups. So we can apply another load. Let's add a new one, some sort of dead load. Apply it in the same way, 1, 2, 3, 4. Let's do a one-way in this case, and a pressure of 0.1. We'll call this a dead load. And we can see the direction that's being applied to. If we want to change that direction, I'll just select that area load and we'll change the column beam direction to being 1 to 4, whereas right now it's 1 to 2. So we'll do 1 to 4, and that will then apply the one-way load in that direction. A really helpful feature in here as well is if we did introduce some other member, so say I'm just going to scroll my loads down, and say we introduced a internal member here, so I'm just going to highlight those two and hit span members, 2 spacings. So it's introduced a new member there. If I was to then apply back in the other direction, 1 to 2, it's automatically identified that member and is now considering that in the tributary area. So that's really helpful if you're making modifications to your file. Using area loads is a great way to automatically reassign and recalculate the tributary areas and the forces required to be added to those members. So you can see now we have some dead load, some equipment load. We can go and turn the self-weight on for the structure, and yeah, pretty happy with some of the loads that we've applied. You can add some load combinations if you want to test different scenarios. In this case, we're just going to do a simple analysis, so we're not going to add any load combinations, but that obviously is a really useful feature when testing different combinations. Okay, so now we are ready to solve, so I'm just going to go ahead and run an analysis. Now with cables in particular, we do a nonlinear static analysis and consider the P delta effects in the cables. And just a note on that too, so in this software what we are doing is segmenting this member into smaller elements to analyze, to perform a cable analysis on. But for convenience, we're maintaining that this is a single element. So in some software, when you define this as being a cable, it will break up this element into a whole, into smaller elements, which makes the modeling process a little bit more difficult. What we do is maintain that as a single element, but we are breaking up the members into smaller elements. This is all being done on the solver side to make the user interface as clean as possible. So I am going to run a nonlinear analysis here. If I did click linear static analysis, it would just revert back to a nonlinear just because I do have cables in the model. But in this case, I know I wanted to run a nonlinear, so I ran a nonlinear. Okay, so here is a solver warning or a solver fail, and this was to do with the comment I made earlier about the support. So the support is still probably not enough. It's not restraining the model enough to make it static. So we're going to just introduce another support, probably in this X direction, just to maintain stability in the model. So let's give that a shot. now. So what we're going to do is introduce a support here. So I can just right click this node and go add support. And we can just do a roller support, which is fairly released. So it's just fixed in the X and Z translation. So in both directions, X and Z, but it is free to displace up and down. So we should see that come through. So that will just give the structure a little bit more restraint in that X and Y, sorry, the X and Z direction, which is probably causing the solver to fail. So I'm just going to go ahead and try that again. And you can see now that that has solved, and we've gotten very little convergence error, so less than 1%, which is good behavior from the solver. And we should be able to review some results coming from the analysis. So I usually check displacement first, just to review my connectivity and just see how the structure is deforming. I can see my cables are behaving in a very expected way. They are sort of sagging down, and we should see that there's a lot of tension in those cable elements. So I can see I've got 6.3 kip force in tension in those elements, which is exactly what we'd expect. And then we can sort of see some compression here, and then further tension in the rest of the frame. So we can also look at stress. So these cables, let's just highlight them, and let's look at some axial stress. So this is obviously a very important part of cable design, is just ensuring that the stress is not exceeding some capacity in the tendons. So it's looking at about 8 KSI magnitude, and also just have a look at the summary. So if I did have more relevant material yield or material strength, then this would obviously come into play here as well. So it's checked all my different load combinations. If I did have any like combined effects, it would also check those and just tell me what the worst case stress is in the tendons or in the entire structure. I can see this is actually a W6/9, so the most stressed element in the structure isn't even one of the cables, it is one of the elements, one of the members. So that's looking pretty good. Another thing I can do is just review some custom limit. Maybe I want to see anything that is exceeding sort of a 7 KSI pressure. So that's a really helpful indicator to tell me what might be failing by providing a custom limit to highlight in the model. So yeah, a few handy post-processing features that help the user identify where my design is at and whether the cables are able to withstand the pressure of the forces on them. Now, if you are having problems solving the model, there's a fair few different things we can try, and we do have an article in our documentation, so I'll just go to documentation, and if I search cables, should bring up all the different relevant articles for cable analysis. So it's got some more information on P-delta analysis, more information about the stability, which we kind of addressed a little bit during the solving process. We've also got some troubleshooting articles. These are really handy, and further kind of detailed articles on how to solve cable structures, particularly when they're not converging. So a few things we like to look out for is just checking the cable diameter, that it is a reasonable diameter. So making sure that the cable diameter, if you put it in too thin, might create instability and cause the P-delta solver to not be able to converge. Check the cables aren't overloaded or underloaded. If there's not enough tension in the cables, they will struggle to solve, and likewise if there's too much tension or if they're overloaded, you'll get some convergence issues in the solver. So These are some things to look out for. You can also reduce your convergence accuracy. So right now it's by default it will be at 1%, but you can increase that if you just want to get some results, or maybe it's just a little bit over 1% and it's just being a little bit too sensitive. You can increase your convergence accuracy to say 3 or 4%, and that should help your model solve or give the p-delta analysis more of a chance to converge on a result. Adding extra supports, which we did demonstrate, just making sure that the structure is stable and static in all the different planes. That's another important troubleshooting method. And then just checking your other members, so checking that there's no buckling or that some of the other members aren't too thin or too slender. It's kind of part of the process of going back and forth between the renderers, just reviewing the model that logically all the inputs make sense. And I think that's a really important part of the process in general when doing structural analysis, but particularly when you have cable elements in your structure. So I can just escape to get back to that and review the last of my model, but I'm pretty happy with how that's progressed. I was able to analyze and get some results out, and review some of the stresses in my cable elements. So we hope you find this tutorial useful. If you have any questions, feel free to drop them in the comment section below. Otherwise, we look forward to seeing your cable structures come through on the platform. Thanks.